Hello again. This is Math 2-115 coming to you from the College of DuPage, and the title of this lecture is Fibonacci Identity Induction Proof. This is my solution, a solution. And as always, please be an attentive learner while watching this video. Recall in mathematics, Fibonacci numbers, commonly denoted by f sub n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. So you see the first few Fibonacci numbers are 0, 1, and then if I add those, I get 1. I add these two, I get 2. I add these two, I get 3. I add 2 and 3, I get 5. If I add 3 and 5, I get 8. If I add 8 and 13, I get 21. If I add 13 and 21, I get 34. If I add 34 and 21, I get 55. If I add 34 and 55, I get 89. If I add 55 and 89, I get 144, and so on and so forth. Okay, so that is, we start with f sub 0 equaling 0 and f sub 1 equaling 1. And from there on, I find the nth Fibonacci number by adding the two preceding numbers for all n greater than 1. Now I ask you to use math induction to prove for all n greater than 1 that this is a closed form for the Fibonacci numbers. That is, f sub n is equal to 1 over the square root of 5 times the whole of, the first quantity is 1 plus the square root of 5 over 2 raised to the nth, minus the whole of 1 minus square root of 5 over 2 raised to the n. So let's begin. And using math induction, we show that it's true for 1. And then we assume that it's true for the numbers between 2 and n. And we show it must be true for n plus 1. So let's start with the expression written larger here, and this is what we say for every n greater than 1. Now I really want to tell you that we could have started at 1, because what happens when n is 1? Well, when n is 1, what happens is we put the, in fact it's really even true for 0, I guess, because this raised to the 0 is 1. And this raised to the 0 is 1. That's 1 minus 1, which is 0. So this is actually true for f0 because f0 is 0. But let's look at 1. If we put an exponent of 1 in here, I will have 1 over the square root of 5 on the outside, but then I will have 1 plus the square root of 5 over 2. But then I subtract 1 over 2, so the 1/2s cancel. And here I have a minus times a minus, so I get 2 times the square root of 5 over 2. But 2 times the square root of 5 over 2 is the square root of 5. And I divide the square root of 5 by the square root of 5, I get 1, which is the first Fibonacci number. And you actually can show that it's true for n equal 2. Because if I square this and square this, what will happen is that I will get the square root of 5 here. Do the calculation and you'll see that's true. And I divide by the square root of 5, I get 1, which is f2. We didn't have to do this step, but I wanted to show you that algebraically it was there. It gets more complicated, and I did ask you to show it by induction. So let's assume then, and this is using the more powerful property of math induction, because we do 2 steps in this regression algorithm, not regression algorithm, in this recursion algorithm. And so it makes sense to use this. So we're going to assume that f sub n is actually equal to this, and that's true for 2, for n between 2 and capital N. And we need to show then, after assuming this as our induction hypothesis, that f sub n plus 1 is equal to, and if I put n plus 1 in instead of n. So this is what I must show. This is my induction hypothesis for the induction step. Now, since Fn plus 1 here is a Fibonacci number, it is F sub n plus F sub n minus 1. Now I'm going to substitute what these are in terms of Fibonacci numbers, and I am assuming that that's true for every for 2 up through capital N, so certainly it's true for these two. So here is the expression that we're assuming by the induction hypothesis for F sub n. And we're going to be adding, this is the expression that we're assuming true for F sub n minus 1. So now we're going to do some calculation. So here's the 1 over square root of 5, but now I'm going to move some things around. So I am going to take this minus 1 minus the whole of 1 minus square root of 5 over 2 to the n, and I'm going to move it over here. Now notice that I didn't change anything, I just changed the order, and it is still a minus because this minus gets distributed. And I'm going to take this one, which is plus 1 over square root of 5, 1 plus square root of 5 over 2 whole to the n minus 1, and I'm going to move it over here. So I'm basically swapping these two. Now when I do that, what I have is an expression that looks like this. Now what I'm going to do is I'm going to factor out a common factor, and I'm going to factor out this as a common factor. 1 plus square root of 5 over 2 to the n minus 1. When I factor that out, I'm going to have 1 over square root of 5 times this. And then what happens is here I'm just going to have plus 1. And over here I have, instead, I need to have, when I multiply this, has to be the power n. So this is 1 plus square root of 5 to the n minus 1 over 2. So this must be 1 plus square root of 5 all raised to the 1 over 2, all raised to the 1 plus 1. And similarly, over here, I'm factoring out this term. So this is going to be minus 1 over square root of 5. I pull that out on the outside. Then I'm going to have plus 1 here. And this is raised to the n minus 1 power. If I take it times 1 minus root 5 all over 2 to the 1, I will have that. So I have this expression. Now, if I get a common denominator here of 2, I'll have 1 plus the square root of 5 plus 2 over 2, which is 3 plus the square root of 5. And similarly, when I get a common denominator here, I'm going to have 1 plus the square root of 5, and then the common denominator top and bottom by 2. So this becomes 3 minus the square root of 5 over 2. And now here's where you have to do a little bit of algebra and perhaps look ahead. You see, what I really would like to have happen here is I'm trying to show that this is true. I started with f sub n plus 1. This is what I'm to show. So you see, this thing has to be 1 plus the square root of 5 over 2 squared. And this thing over here must be 1 minus the square root of 5 over 2 squared. And do the calculation. If you take 1 plus or minus the square root of 5 squared, you get 3 plus or minus the square root of 5 over 2, which is exactly what we need. So what we're going to do is we're going to do equal. We're going to substitute this for the plus and this for the minus in the middle. And now we're going to use properties of exponents. And so the exponent of n minus 1 plus 2 is n plus 1. And the exponent of n minus 1 add 2 is n plus 1. So we have shown that this f sub n plus 1 is equal to this. Therefore, by the principle of mathematical induction, the strong form, we have shown that This expression is true for every n greater than 1. In fact, we showed that this is true for 0, 1, and every n actually greater than or equal to 0. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. Self-care is important, and we're all on this together. May God bless you all.